Hello everyone. Today I continue subject of discrete probability and the basics of it, which we are studying. We started studying last session. So let me first recall some basic notions which are very important. Uh, our terminology. An experiment was an act that we performed with some output, and we wanted to compute the probability of a certain kind of output. Sample space was the set of all possible outputs or the outcomes. For instance, an experiment is flipping a coin or rolling a die, or flipping 10 coins at the same time, or rolling 3 dice. Then we had an event. An event was simply a subset of sample space. And the event was the outcomes that we wanted to compute its probability. For instance, when we flip 2 coins and we want the outcome that one of them is head and one of them is heads and one of them is tails. And in this case, our event will be the set of all the outcomes where one of the coins has shown up heads and the other tails. So this is the wanted outcomes, I would say. And then the probability of an event E so let's denote the event by E. And the probability of E, by definition, was the number of objects, number of elements in the set E divided by the number of elements in our sample space. So the ratio of the number of outcomes that are wanted, or uh, that you are interested in, to all of the outcomes. We want now to compute probability of the outcome of a subset of a sample space. So let S E be as before, and let E1 subset of S be some event. Then recall that the complement of E1 with respect to S is the set S minus E1. This is again an event because this is just the this is a set set of outcomes with a subset of S. E1 bar is also a subset of S, and therefore is a new event. And let's compute its probability. Is by definition the number of elements in E bar divided by the number of elements in S. And because this is the complement of the set S, and whichever whatever element is in S and is not in E1 is in E bar. Therefore, we have that this is cardinality of S minus cardinality of E divided by cardinality of S. And this will be 1 minus cardinality of E divided by cardinality of S. And this is 1 minus probability of E. So this is totally expected intuitively. So here is an example that will be easily solved using the probability of a complement. A sequence of 10 bits is generated randomly. What is the probability that at least one of these bits is 0? So you know that the sequence of bits is, so we have 10 places, and the example says that each of these places is filled by 0 or 1 randomly. So this means either by a computer who generates random numbers, or for instance, we can flip a coin 10 times and record what is the outcome, and we assign 0 to be the tails and 1 to be the heads, for instance. And in this kind of situations, for yes, so and then the question asks, what is the probability that at least one of these bits is 0? And so the experiment is again clear. Our sample space is the set of all 0, 1 sequences of length n. I'm sorry, of length 10, right? Because when 10 bits are generated randomly, we could generate all possible sequences of 0, 1 of length 10. And so let's already compute the cardinality of the set S, but we know that because each cell here has 2 places, we have computed also before the total number of sequences, binary sequences of length 10 by the product rule is 2 to the 10. And the event that you're interested in is the set of sequences with at least 1, 0. All right, it can be computed, but let's do a trick and let's compute instead of E the probability of E bar. And what is here E bar? So let's interpret it. E bar is by definition any sequence in S which is not in E. But that means that it is a sequence is in E bar when it does not have at least 1, 0. Okay, when a set does not have at least one zero, means that does not have any zero, and therefore it has to be all ones. All right. So therefore, this is the sequence. And this is happens only for one sequence, and the cardinality of either 4 is 1. Now the probability of, E bar, and the probability of E bar is therefore 1 over 2 to the 10. And we know from previous slide that the theorem, the probability of E is 1 minus 1 over 2 to the, using the previous theorem, that probability I write it here. So this we proved the last slide. Probability of E bar is 1 minus probability of E. We have another theorem which is for the probability of the union of two events. So that's E1, E2, B, two events. Then probability of E1 union E2 is probability of E1 plus probability of E2 minus probability of E1 intersection E2. So first let's see what this means. So these are events, so these are subsets of sample space. This here is the union of the two events, is again another event. E1, E2 is event, E1 intersection, E2 is again another event. So therefore we can compute these probabilities. And I want you to think about this picture that we had before of the cardinality of the union. And note that this division by the cardinality of S that happens for all of these that we have to do for all of these probability computations is it's division by a fixed number, which is the cardinality of S. And it is important that what's the relation of cardinality of these EIs together. And then that will give the same relation between the probabilities. So let this set, this square, sorry, this rectangle here be S, and let this one be E1, and here let it be E2. And you remember that from before we knew that the cardinality of E1 union E2 for any two sets is cardinality of E1 plus cardinality of E2 plus minus cardinality of E1 intersection E2. And you see, this is a very good way of thinking about probabilities. So the set S here is fixed, and the cardinality of it is everything which is in here. And the probability of any subset of S, like E2 for instance, is the ratio of elements which fall in E2, and the ratio of those elements which are in 2 to the all the elements in S. So this area over all the area. Yes, and this is true for any subset in very strange shapes, which happens here. And if we just write down the definition, what is important is not the constant S, but the cardinality of the set. And we knew from before the cardinality of E1 and cardinality of E2, the number of elements in the union is the number of elements in E1 plus the number of elements in E2 minus the uh, number of elements in here that we have counted twice. And we remove one instance and we have counted them once. Now so you just subdivide this relation with S. So that's why I'm saying that the S is constant, it's not important, so I can just subdivide all of both these sides with S. And then this will give me, sorry, with cardinality of S. It's a non-zero number, therefore we can subdivide, and then it gives exactly what we wanted. Recall that when we define the probability of an event to be the cardinality of E divided by cardinality of S, we use the assumption that every outcome in S is equally likely to happen. And therefore, the probability that E happens is the ratio of the elements in E divided by elements in S. That was the assumption up to now, and it simplifies a lot of computations, but this is not the real thing that happens in a lot of applications and a lot of problems and where probability theory is used. And it is very important to deal with situations where some outcomes have more probability of happening than other outcomes. In this section, we start the mathematical theory of probability, which is more general than the simple cases we saw up to now of the all outcomes having the same probability. So let me now uh, start this section, but I just want to say that what we add to what we knew previously is the function little p that goes from the set of the sample space into the numbers between 0 and 1. So let me write that as interval 0, 1. So this notation is the interval 0, 1. That means the numbers between 0 and 1. Real numbers between 0 and 1. Now we call P a probability distribution over S if P satisfies the following condition, that the P of S, little s, is the value that the number that P assigns to S, so that is the probability of S, and we want that the sum of the values of P at S over all the elements of S be exactly 1. Right. So we take any function P from our set of samples to 0, 1, and this now replaces the probability of any outcome. So this little p gives us the probability of any outcome, and that's why it's called probability distribution, because it distributes this whole possible, all possible probability, which is 1, over the any single elements of our sample space. Yeah, so it has to assign to any sample a real number between 0 and 1, and it has to sum to 1 over all these samples. So these two are the important properties of a probability distribution. Of course, this is a discrete probability distribution, and this summation here makes sense only if S is finite. Otherwise, or if S is infinite, it has to be that only a finite number of elements get non-zero probabilities, because you should remember this, that an infinite summation of non-zero elements is meaningless. So this sigma is only defined when you have only a finite number of non-zero elements. Otherwise, the summation is not uniquely defined. So you should remember this. And so S is either therefore a finite up, as we have seen up to now, and which is most often the case, or if it's infinite, those outcomes which have non-zero probability are finite. Let us now see the simplest probability distribution. So let's see P sub u. First, I should say we have some sample space whose cardinality is exactly n, so it's finite. Then define. So let's see P sub u from the function from S into 0, 1. It assigns to any element the value 1 over n. And it is now clear that the sum of the P sub u over all the elements of S becomes 1, and therefore it's a probability distribution. And this probability distribution is called the uniform distribution. So it distributes the probability uniformly over all the outcomes. And this probability distribution is the probability that we assumed in the first section when we computed the probabilities by the cardinalities. And we assumed that every outcome is equally likely, and therefore we were implicitly assuming the uniform distribution. Okay, now that we have the little p So we should define now the probability of any event. So let S be sample space and E subset of S an event. The probability, okay, we want also that let little p be a probability distribution then the probability of E is by definition, so this is the definition of the probability that is given by the probability distribution P, and that is as expected the following. So the big P of E is summation over all, let's say, x's in E, probability little p of x. And this is the summation of the probabilities of elements of E. When we had the uniform distribution before, each of these, the P was 1 over n, which n was the cardinality of S. So P was 1 over cardinality of S, and this number were equal to cardinality of E divided by cardinality of S. But now that the elements of E have different probabilities of happening and are not equally likely to happen, we just sum the probabilities of elements of E. And so you should take this definition regardless of, you should provide yourself with an intuition of why this is the probability of E intuitively, but this is the definition of probability of E with respect to the probability distribution E, the little p. We have now a very useful theorem. Let E1, E2, E3 all the way to infinity be a sequence of events assume that for any two EI, EJ, we have AI intersection EJ is empty. And this is, if you remember, if EI, EJ are disjoint, that's the same. So this means that for any two of them that are disjoint, it means that there is no element of, there's no sample or there's no outcome that happens in more than one of these guys. And then if we have this condition, the probability of E1 union E2 union E3 is sum of the probabilities. So this is, by applying the previous definition, because these are just summations. So apply the definition of the probability for this union, and that is the summation of little p over all the elements of these sets. And because these elements, these sets are disjoint, you can break that summation into summation for the elements of E1, summation for elements of E2, summation for elements of E3, and then rewrite that summation as like this. And most often we are interested in this formula when the sets EI, there's just a finite number of these sets, and when there's infinite n, again, most of them, they are these, they should repeat or something like that. But the interesting case is really when there's a finite number of cases of events, and this formula then can help us a lot. And let me write now special situations. So consequences of this theorem is that, again, probability of the complement of a set is plus the probability of the set itself is because E and E bar are disjoint from each other, and their union is S, is the probability of the whole sample space, which is 1. And therefore, we have that probability of the complement is, again, as we expect, is the 1 minus probability of the set itself. And we also have the previous formula. That the probability of the union is probability of E1 plus E2 minus the probability of intersection. And to deduce this formula from the above theorem, we should write E1 and E2 as a summation of 3 disjoint sets. Let's say probability, let's say E1 and E2 minus E1 intersection E2. So let's take E1 and E2 minus E1 intersection E2. And these two sets are now disjoint, and the probability of the union of these is probability of E1 plus probability of E2 minus E1 intersection E2. And this here, this term is equal to probability of E2 minus probability of E1 intersection E2. So this Also, you should check by the definition, it usually follows, and of course, this one is probability of even union. And so you should remember that for disjoint sets, the probability is additive. That is very important. So when when you have the union of two disjoint sets, then you can add the probability. So this is called the probability for disjoint sets. Union of disjoint sets is additive. So you should remember this fact, and it's very important. So I end the session here.